So we've just talked about how to define sets of numbers on a one-dimensional plane. Now we're going to move to the two-dimensional plane, which is essentially where we finish off for defining numbers in VCE methods. We have graphs on a Cartesian plane, and we need to describe what the x and the y values are in those specific cases. So we actually have two new terms that are really important and really prevalent in the VCE methods course. You have domain, which is the possible set of values for the independent variable, which is usually x. And then you have the range, which is the possible sets of values for the y variable or the dependent variable. The reason why I say independent variable and dependent variable for x and y respectively is because in a lot of applications, they might ask for the domain of something, but it might not specifically be talking about x. It's just whatever variable is on the x-axis or on the independent axis. Or you can just think about it in general as the independent variable. So we've got a really basic example here, which is most likely something that you won't see in VCE methods, but it's really good to break it down with a really basic example to understand the fundamentals. So in this case, we just have a scatter plot with 4 different points on it. And essentially it's just going to teach us the principles of defining the domain and range. And then we have an actual graph here, which is more of a realistic thing that you might see on a test, let's say. So, go through the first example. We have 4 coordinates scattered on this Cartesian plane. So, you can see that the possible x values, you've got x equals 1 here, you've also got x equals 1 here, so that's a common term. So, what do we do when we have an identical term twice? You have x equals 2 there and x equals 3 there. So, if we want to define the domain, how we do it is we say x is an element of, like just our normal domain definition or our normal variable definition. And then in this case, because we have individual values, we essentially treat it as just a list of individual values. So how we define a list is actually through just a squiggly bracket. I think I might have gone through it in the start of this whole functions and relations course when we talked about the Venn diagram with the A and B, when we had those individual items and we wanted to collate them together, we use squiggly brackets because that's how we define a list. So in this case, we have x equals 1, x equals 1, x equals 2, and x equals 3. Now for the duplicates, we don't include it twice, we just include it once. So we have 1, 2, and 3 for the possible values of our x, which is going to be our domain. So our domain is 1, 2, or 3. The reason why we don't include the 1 twice is just because the domain is on the range as well. It's just asking for the possible values that the x variable can be. So there's no point including 1 twice, even though it is there twice. It's just that 1 is allowed to be a variable, therefore we put 1 in the list. So no point including it twice. Now for the range, I'm just going to write range there. We say y is an element of, because obviously we're talking about the y variable now. So we've got -1, we have 0, and we also have 1 as well. So again, we're going to define it as a list. So we've got -1, 0 is a duplicate, but it doesn't make a difference when we're defining our range, and we have 1 as our final value. Awesome. Now this is not very common, defining values as a list. As I said before, it's more likely that you're going to be defining the values of a function. And the difference between this and this, I mean, it looks different, right? You have individual points here versus a curve, but the difference is that this is a continuous curve or a continuous definition, where this is discrete, discrete meaning that you have individualized values. So let me just write domain and range, and then we'll look at the graph and try and figure out what are the possible values for x, which is going to build up our domain. Now x, we know, is this horizontal axis. It goes from left to right. You can see the most left value that we have is -2, and that's an open circle, which means it's exclusive at that point. And then every value to the right is pretty much defined. So we have, if you go from -2, you can see all the values are defined there. You've got values, 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 and then this arrow indicates that we're going in the positive infinity direction. But we should know from a parabola that it kind of goes on an angle, so it's going in the positive x, but also in the positive y as well. So that'll go all the way to positive infinity on the x-axis. So if we want to define the domain for x, I'm going to use interval notation, by the way, but you can use set notation. I'm not going to do both. I'll just do one, because you should be able to convert between both of them. We say x is an element of, and we go from -2, because that's, again, the most negative variable that we have, and it's a round bracket because it's exclusive, and then we go to infinity. So this will be the domain for this function here. Now, for the range, again, it's the same thing. We're just looking at the vertical values because the vertical axis is our y-axis. Now, a common mistake is that a lot of people would just choose that same point and say that the range goes from 2 to infinity. But that's actually not the case. You might have thought that as well, but it's actually not the case. We have to go from bottom and check upwards. And this point is the most left point or the most negative point for our x variable, but it's actually not the most negative point for our y direction. It's actually the turning point here, which is at 0, 0. So the lowest value that we can have here is 0 for the y-axis. So we say y is an element of, and you can see that can actually include 0, 0 as well, because it's a solid point, it's defined in our function. So we go from 0 round bracket to infinity, and that is correct. Now, a lot of people would look at this and think, oh, well, if it's not defined upwards of 2 on this branch, why would the values be more than 2? It's because on this other branch here, it's defined upwards of 2. So even though this is limited, this side of the graph is limited, this side of the graph is not. And when we're talking about domain and range, it's the possible values that you could have. So you can have values that go above 2 here, even though it's not the same on both sides. So just when you're talking about domain and range, it's always you have to think about it as the possible values. So it's just all values that are used. So that's how I think of it. It's kind of a layman's way of thinking about it. But for the domain, it's the possible x values or all the x values that are used. For the range, it's all the y values that are used. In this case, all the y values are used all the way from 0 all the way up to infinity. Now, honestly speaking, if you look at a graph, it's really easy to determine the domain and range because you can just see what x and y values are used. But what if we're actually not given a graph? What if we're just given the rule of a function and we have to determine what the domain is or what the range is? This is what we call the implied domains problem. Essentially, an implied domain is a domain that's caused by a restriction in numbers. So you might be thinking, what do I mean by that? A really common example of when you have a restriction in what you can do with algebra is when you're dividing by numbers. We know that if you divide by something, it can't be 0, whatever you're dividing by, okay? So I've written this example here. If you have 1 over, let's say this expression here, which I've represented by a square, that square cannot equal 0. So I've got this corresponding example here. Find the implied domain of y is equal to 1 over x plus 1. So x can be any value. It's just the only problem is that the the denominator cannot equal 0. So what I say in this case is x plus 1 cannot equal 0. Therefore, x cannot equal -1. So this is not the domain. It's not all the possible set of values. But we know, based on this calculation or this algebra that I've done, that x can't equal -1. But it can be any other value, right? You can put any other value into x, and it's going to be valid. So what I say is that, therefore, the domain is x is an element of all values. So I represented that using the real numbers, that capital R with that extra line. But I'm just going to exclude -1 from that set. Okay, so this is how I exclude -1. I'm just going to break this down. X is an element of all real numbers. So that's just all numbers on the continuous number line because all numbers can be in there except -1. So I've used a backslash to exclude -1. And I've put -1 into squiggly brackets. Essentially, it's just a list of one value. So it's just -1 in the bracket there. You could do this with interval notation as well, but yeah, that's fine. You could use it whatever notation you want, as long as it's right. Now, hopefully that makes sense, how we find the implied domain and why dividing by 0 actually causes problems with our domain. So that's how we actually deal with the problem. We just find whatever values you can't have, and then we say x can be any value on the real number line except that value or those values that are not valid. Now, another common way of restricting numbers is through a square root. So if you have the square root of a number, we know that you can't square root a negative number. So it can be positive, it can still be 0 as well. So in this example here, we have y is equal to the square root of 2x plus 1. So how I find the domain of this, or a problem like this, is I say 2x plus 1 is greater than or equal to 0. Therefore, 2x is greater than or equal to -1. Therefore, x is greater than or equal to -1/2. And I just put this into set notation because there's a convenient way of writing that. You could put it into interval notation as well. But in this case, what we've done is we've treated whatever's underneath the square root as a positive or 0 value because it can't be negative. So that's what I've done here, greater than or equal to 0, and then just rearrange for x to find my possible domain. Now, the limits of expressions in VC methods or just in algebra in general is not limited to just dividing by expressions or square rooting expressions. Some common, or not so common ones, are log. You can't have the log of a negative or a zero number. So anything within a log bracket has to be positive. You also have tan, which is a really, like a tangent function, which is a really unique one where you can have values everywhere, but then periodically you can't, because if you remember a tan graph, it looks something like this. So it looks something like this, and you've got asymptotes periodically. So let's say if you had something inside a tan graph, or like a tan function, and you had to find the implied domain of it. I'm going on a real big, like no pun intended, I am going on a tangent here, but in this case, you would have a periodic restriction on your numbers. So that's a really unique case. I think we have examples of that in our corresponding worksheets, but you feel free to give that a try. It is a bit more of a tedious one, but it's really important to understand what functions actually limit what you can do, because that's really important for finding implied domain. An example of an operation that doesn't actually restrict numbers is, let's say, like you have y is equal to x squared. We know that you can square any number. If you square a negative number, it becomes positive. If you square a positive number, it becomes positive. If you square 0, it becomes 0. So there's no actual implied domain, or there's no restriction on our implied domain for, let's just say y is equal to x squared, because there's no restriction on the algebra that you can do. And that's actually represented through our graph as well. But if you looked at the graph of, let's say, y is equal to 1 over x, well, what does that look like? You've got values defined everywhere except at x equals 0 line, because that's where our asymptote is. So you can think about it as from an algebra standpoint, and that's what I've done with these two examples here. Or you could also think about it from a graphical perspective. Either way, you're going to get the right answer, but I think it's good to understand both in order to, encapsulate everything that you need to know for implied domains. One thing I want to add before I move on to the next video, so I forgot to mention this in the previous video, is that an implied domain is something that's just the nature of algebra, right? So if you have y is equal to 1 over x, there's no way of making that x equal to 0, because we just can't divide by 0. So that's what an implied domain actually is referring to. It's like a natural exclusion of numbers, but you could also have just restricted domains. Let's just say if you have a problem where you can't have x is less than 0, although algebraically it's fine, sometimes you just don't want those values to exist. So a really common example of that is if you have an example with time. A lot of circumstances that you have function, or let's just say you have an equation and you don't want the time to be negative, a lot of the times it would just say time is greater than or equal to 0. So that's what we call a restricted domain, and that's the nature of a problem, right? So another time is if you're talking about money, a lot of times you can't have negative money. Like let's say if you have your bank account, if it's not a credit card, you can't have negative value in that bank account. So there'll be another time that you have a restricted domain on your numbers. So you have there's two ways that numbers are restricted. One of them is through implied domain, which is to do with the rule. And then the other one is just a artificially restricted domain, which is a result of the specific problem that you have.